Hello and welcome. We are going to be looking at the warm-up exercise for cost functions. This is just sort of an introduction or a reminder of how sort of the general cost functions and step counting works, and then we'll get into more complicated examples in future videos. So we're going to start with how many steps are required by the following program. And as discussed in class, we're going to always make sure that we're starting with that inner loop as a place to begin this conversation. So I'm just going to highlight the lines that I care about. From here, I'm going to count each of these as one line. And just for my own sanity, I don't want to forget the one time that I have to count this when it's false. So what I can see is on one iteration, that doesn't spell iteration. We'll do it down here. One iteration is equal to 3 steps. So then the question we have to ask ourselves is, of course, that summation, how many times does that 3 steps occur? Well, it starts with k equals 1, and then we see k going up by 3 each time on line 5. So we better actually take a second and figure out what that means for the number of times that this is going to run. So if we look at our precondition up here of what n actually is, n is greater than or equal to 3, and it's always going to be a multiple of 3. So this is what our n's might look like. And we're going to make some kind of a j that's going to represent our number of runs. So we're going to do something like this. So the first time that this starts, k will start at 1, and then k will go up to 4. But of course, it doesn't run when it goes up to 4. So this inner loop is only going to have ran one time in that scenario. Next time, k starts at 1 and then goes up to 4. So it will have run 2 times. K goes up to 7 and up to 10. And we can see a pattern starting to emerge here. Now, there's lots of different ways to now sort of address that in our summation, but we definitely see a pattern emerging. So let's say let j equal, and what we see j being equal to is going to be n over 3. I guess more specifically, we actually want j to start off at k, and it will go all the way up until that n over 3 run time. Now, we're going to actually want to start our j off at 0 if possible. So let's make this equal to k minus 1 so that we can get our j starting at 0. But if we're going to take 1 off on that side, we're also going to need to do the same over on this side. So what that allows us to now write for our summation is going to be j starting at 0 up to n over 3 minus 1. And we can put that 3 right there. Now, when we factor out our 3, we end up with something that looks like this, n over 3 minus 1. And this allows us to, of course, use our identity. So we end up with 3 n over 3 minus 1 minus 0 plus 1. These are going to cancel themselves out. And we end up with 3n over 3, which of course is just n. Now, before we finish off, we don't want to forget about that plus 1 that happens for when the while loop is false. So let's add a plus 1 for when while false and it stops. Just as a reminder, we'll write that right there. So now we have this part of our code right here coming up as n plus 1. The next piece of this and final piece, because this one's not too bad at all, is to look at these 2 lines and recognize that each of these counts as a single step. So now all lines of code have been highlighted in our function. So we can say that f of n is going to be right here. F of n is going to be equal to, we'll grab those 2 lines of code plus our loop. So we end up with n plus 3. And so that is our final answer for this problem. Join me in the next video where we're going to start working through much more complicated examples. Thanks, everyone. Bye.